Welcome to the video for problem 310 of Engineering 623. Let's start by reading this problem. You see a picture here at the beginning, but the statement of the problem says, consider the partially filled parallel plate waveguide shown on the accompanying figure. Derive the solution, and that in parentheses it then says fields and cutoff frequency, for the lowest order TE mode of this structure. Assume the metal plates are infinitely wide. Can a TEM wave propagate on this structure? So it turns out that this problem is rather lengthy in terms of the algebra, but it's not too terribly hard to understand what's going on. So let's go ahead and get started with this. In your book, you see that for the TE modes, you have these equations giving HX, HY, EX, and EY in terms of HZ, since this is a TE mode. EZ would be 0 in this case. Now, the KC squared, which appears in these equations, is equal to K squared minus beta squared. Now, beta will be the same in all three of these regions, but K, of course, will not be. Where epsilon is equal to epsilon naught, K squared is just omega squared over C squared. But where epsilon is equal to epsilon r epsilon naught, then K squared will be equal to the quantity epsilon r omega squared over C squared minus beta squared. Now, the boundary conditions that we must consider for this problem they occur, of course, at the upper and lower metallic plates, and also at the dielectric discontinuities at x equals plus and minus W over 2. And so the boundary conditions, some of the most salient boundary conditions are EX equals 0 at Y equals 0 and Y equals D, because EX is a tangential component of E at Y equals 0 and Y equals D. EY is continuous at X equals plus or minus W over 2, and again that's because EY is a tangential component of E at X equals plus or minus W over 2. Likewise, HY is continuous at X equals plus or minus W over 2. Epsilon EX is continuous at X equals plus or minus W over 2. HX is continuous at X equals plus or minus W over 2. Now, this third boundary condition about HY being continuous at X equals plus or minus W over 2, when we look up here for HY, it is we see that the formula for it is minus J beta over KC squared partial HZ partial Y. Now, as we have already said, beta will be the same in every region, but KC will not be. So when we say that HY is continuous at X equals plus or minus W over 2, that's the same thing as saying that 1 over KC squared partial HZ partial Y is continuous at X equals plus or minus W over 2. And that is noted here. But boundary condition 4, which governs epsilon EX, well, EX is minus J omega mu over KC squared partial HZ partial Y. Now, of course, J omega mu all of that is constant everywhere in this problem. So this is really the same as 1 over kc squared partial hc partial y being continuous. But remember, now we have epsilon times that. So we have that BC, the boundary condition 4 implies that minus j omega mu times epsilon over kc squared partial hc partial y is continuous at x equals plus or minus w over 2. In other words, getting rid of that j omega mu, epsilon over kc squared partial hc partial y is continuous at x equals plus or minus w over 2. Now we know that epsilon is discontinuous at x equals plus or minus w over 2, and from boundary condition 3, we have that 1 over kc squared partial hc partial y is continuous at x equals plus or minus w over 2. So when we multiply something that's discontinuous by something that's continuous, we should get something that's discontinuous. So that's how we conclude here that epsilon over kc squared partial hc partial y must be discontinuous at x equals plus or minus w over 2, but that disagrees, that's in contradiction of boundary condition 4, unless 1 over kc squared times partial hc partial y is equal to 0 at x equals plus or minus w over 2. So in view of this information that 1 over kc squared partial hc partial y is equal to 0 at those 2 points, that makes us consider the solution that maybe partial hc partial y is just 0 everywhere. In other words, maybe hz of x and y is really just hz of x. We don't have, for hz in the transverse plane, now of course, remember, we've already taken out the dependence of hz on z, which is e to the minus j beta z. But in the transverse plane, we're saying here, maybe we're going to consider the possibility that hc does not depend on y, it depends only on x. Now recall that this is from your book, the equation for hc is partial squared hc partial x squared plus partial squared hc partial y squared plus kc squared hc equals 0. Now, by the way, and we'll come back to this later, but boundary condition 5 implies the same thing as boundary condition 2. So just keep that in mind. So anyway, if hz does not vary with y, then this equation just becomes the simpler equation d squared hc dx squared plus kc squared hc is equal to 0. And in view of that, then, our solution for hz in the various regions is c1 e to the j kc1x for x less than negative w over 2, c2 e to the, well, there's no need to read it off, but you have this solution for x between minus w over 2 and w over 2, and then finally this expression for x greater than w over 2. And I might as well go ahead and point out here that if omega is chosen in such a way that kc1, and in fact omega should be chosen in such a way that kc1 is imaginary, so that we have decaying fields in the region x less than minus w over 2 and x greater than w over 2. Well, notice that when kc is imaginary, we want the negative imaginary value rather than the positive imaginary value. You can see this so that we will have decaying behavior both in the region x less than minus w over 2 and in the region x greater than w over 2. And here's exactly what I'm talking about here. If omega squared over c squared is less than beta squared, then this is a square root of a negative number, and we want to take the negative imaginary root rather than the positive imaginary root. Now that we have that proposed solution for HZ, we can check the boundary conditions, and it's easy for 1, 3, and 4. Those are all automatically satisfied since our HZ does not depend on X. Does not depend on Y. 2 and 5 both imply that 1 over kc squared partial HZ partial X must be continuous at X equals plus or minus W over 2. And of course, we also have to ensure that HZ itself is continuous at X equals plus or minus W over 2. So we have 4 equations. Okay? At minus W over 2, we have this equation. This first equation, number 1, is for continuity of HZ. And the second equation guarantees continuity of both EY and, let's check this again, and HX, EY and HX. Because again, remember 2 and 5 imply the same thing, so EY and HX. So equation 2 here implies the continuity of EY and HX at X equals minus W over 2. Number 1 implies continuity of HZ at X equals negative W over 2. And then number 3 implies continuity of HZ at positive at X equals positive W over 2. And number 4 guarantees continuity of EY and HX at X equals positive W over 2. So these are the 4 equations we're going to be working with now to get some interesting results, but it does take some work. For convenience, I'm going to introduce these 2 parameters, lambda 1 and lambda 2. Using those makes these 4 equations look much more compact, as you can see right here. And then we're going to do some algebra to reduce those 4 equations to just the 2 equations, 5 and 6. And then we're going to divide 5 by 6 to get this equation 7. Now, once we get equation 7, we cross multiply to get this equation, and then once again cross multiply, and we end up, after all of that, with just the simple conclusion that C3 squared is equal to C2 squared, which of course means that C3 is plus or minus C2. So when C3 is equal to C2, that's referred to as the even solution. When C3 is equal to negative C2, that's referred to as the odd solution. For the rest of this lecture, I'm going to discuss the even solution, and then perhaps we'll have a homework for you to investigate the odd solution. But for the even solution, again, now that's C3 equals C2. So if we substitute the equation C3 equals C2 back into these equations 1 through 4 that we started with, then we get equations 1 prime through 4 prime, which look like this. And if you look at these equations 1 prime through 4 prime, you'll notice that if you look particularly at 1 prime and 3 prime, that the right-hand side of those equations are the same. So if the right-hand side is the same, the left-hand side must be the same as well, and so we easily can conclude simply that C4 is equal to C1. Once we substitute C1 in for C4 into equations 3 prime and 4 prime, then we see that 3 prime becomes identical to 1 prime, and 4 prime becomes identical to 2 prime. So now, in other words, once we substitute C1 for C4, we see that really we only have 2 remaining equations, 1 prime and 2 prime, rather than 4 equations. So now we're going to divide 1 prime by 2 prime to get this. And once we do a little bit of trig here, we end up getting the equation this form. And now finally, let's recall what KC1 and KC2 are and substitute in. And again, what we're going to do is we're going to consider values of omega that would make KC2 real, but KC1 negative imaginary. And so, in other words, what we're going to do is we're going to consider omega that will make epsilon r omega squared over c squared greater than beta squared, but such that omega squared over c squared will be less than beta squared. And therefore, this highlighted equation with the asterisk by it will become this. And this is called the transcendental equation governing the even solution. And the condition for omega that will make this solution valid is omega squared must be less than beta squared c squared, but greater than beta squared c squared divided by epsilon r. So that tells us what we want to know about this solution, and that's all we need to say. I guess I can say one more thing. So that concludes the discussion of the TE once I guess I should say not quite, because now we need to go back and investigate the odd solution, but that will be done as part of a homework. I will go ahead and answer the question, is there a TEM mode for this structure? And the answer is no, and the easiest way to see that is the following. Remember that for the TEM mode, beta squared is equal to k squared, and which is of course omega squared over c squared. So if beta squared were equal to omega squared over c squared, we can see that excuse me, let me say it this way. If beta squared were equal to k squared, then there's no way that beta we could have phase matching at x equals plus or minus w over 2, because the value of k there as we go from one region to the other is not the same. So and of course for the TEM mode, beta is equal to k, and so if k is not continuous, then beta would not be continuous, and therefore we could not have a TEM mode. But as we have seen, we do have a TE mode, and we've seen we've investigated here the even solution for the TE mode, and perhaps for homework we will investigate the odd solution. But that concludes our discussion of problem 310, and so that's it.